Hello everyone, and welcome to video number 5 for lesson number 11, where we're talking about the definite integral. And these last 4 examples that I'm going to do with you guys is just going to reiterate what we've talked about in videos 3 and number 4. So let's go ahead and start with example number 9, where it says let f be a continuous function on the closed interval from 0 to 2. If f of x is in between 2 and 4, what's the greatest possible value of 0 to 2 of f of x dx can be? Now, we did an example in the previous video, and I'm going to show you that to you now. It's actually example number 7, where we had to use this theorem right here, property number 8, to estimate this value, 1 to 4 of the square root of x dx. And I told you guys in the video that this is not something that you most likely will be assessed on, because you can easily find this using the fundamental theorem of calculus, which we're going to talk about in the very next video. Well, let me go back to number 9 now. Well, this is a question that you should be able to do now that you know that property. So it says, what is the greatest possible value? This can be right here. So we know that based on the theorem that we had, that the greater or upper bound of our function is going to be what you see here in this value right here. Yeah, and the lower bound I could also write down as the little m b minus a, but I don't need this part, right? I only care about this because I only care about the greatest possible value this can be. Well, let's figure out what this is. Well, m is going to be the 4, right? That's the highest value that f can be, or f of x can be, so that's going to be 4. Remember, we plugged in a value, so f of 2, the highest number here, is going to be at least equal to 4, or maybe less than. This b and this a, well, our interval is going to be ab, well, that's going to be 0 to 2, so this is going to be 2 minus 0. So this integral must be less than or equal to this number, and this number is actually equal to 8. So that's how you solve that problem. Okay? So using that theorem. Is it practical? No. Is it a question you'll see on the exam? I'm pretty sure not, but I have to cover everything to make sure that you guys are fine with you taking the exam. Okay, so let's look at example number 10. Example number 10 says find the area under the curve. So we did this question again from the previous lesson, previous video, example number 8. So let's look at this. Now this one we're not given very much. We're given a semicircle and we're going to give a triangle. And the directions you usually would say, given a semicircle and triangle, find the area under the curve. So the first thing is we want to find the area of the semicircle. So let's actually look at that first. So if we want to find the area of the semicircle, that's my semicircle picture, then we're going to go and integrate from 0, and we're going to call this function f of x, like why not? So 0, so we got to figure from 0 to this point right here. Well, what is that point? Well, we have a semicircle, and we know the radius is actually equal to 3, right? We're given that. So that means that this is also 3, and this is 3. So this point right here is going to be 6. So we're going to integrate from 0 to 6 this semicircle. And remember, all we have to do to find this is just find the area of this semicircle, and that's going to give us this value, right, from 0 to 6. How many times more am I going to say semicircle? I'm sure I'm saying that quite a bit. So, well, what is this area? It's going to be 1/2, and then the area of a circle is going to be pi r squared. So the 1/2 is half of the circle, so pi, and then our radius is going to be 3, and we're going to square it. So this area is going to be 9 over 2 pi. So that's going to be the first part of our answer. All right, and now we want to find the area of this triangle, right? We want to find the area of this triangle, and again, we know the area of the triangle is going to be negative because it's underneath the x-axis. So the area of a triangle is going to be from 6 to 9 of f of x dx, and we know this value is going to already be negative, right? It's already going to be negative. So it's going to be 1/2, and then our width, or our best as our base, is going to be 3. Right, from 6 to 9, and then we have right here that the height of this thing is actually -4. So I'm going to go ahead and just put a 4 here because we already have the negative in front of it, but it's going to be -4. So we're going to have 12 divided by 2, and then we're going to subtract, or make it negative, it's going to be -6. So this answer, ladies and gentlemen, is simply going to be just a combination of these two things. So this answer is going to be 9/2 pi minus 6. And that's it for that question. Okay, so now let's move on to the next question. I really like example number 11. I think it's really, really great. So question number 11 says a graph F is made up of lines and semicircles, and see, you guys can see that here, right? So lines and semicircles shown to the right. And it's telling us that f of x is equal to the integral from -1 to x of f of t dt. And so we want to find f of 5 and f of -5. So let's first of all find f of 5. Well, f of 5 is going to be equal to the integration from -1. And so since x is 5, we're going to plug in 5 right here. So it's going to be the integration of -1 to 5 of f of t dt. And this graph right here is going to be f of t. So from -1, which we're going to see right here, so we're going to go from -1 all the way to +5. So I want the area of this trapezoid, or this triangle, and I want to subtract the area of the semicircle. So that's really all that we're going to do. So we've done this quite a bit, so we're going to go ahead and just do this one and not spend too much time on it. So the area of this triangle would be 1/2, the base is going to be 2, the height's going to be 4, and I'm going to subtract the area of the semicircle, it's going to be 1/2. We're going to have pi, the radius is going to be 2, and we're going to square that. So we're going to get the answer to this problem. It's going to be 4 minus 2 pi. Okay, so that's going to be the easy one. That one we've done many times before. Okay, so now let's look at actually f of -5, right? F of -5. So we're going to go -1 again, and we're going to plug in -5 here. We're going to do -5 of f of t dt. Now the first thing we're going to do is we're going to apply one of the theorems that we used before. Remember, we want this number here to be the smaller of the two, right? We want that number to be smaller of the two. So in order for us to fix this and make this a -5 here and a -1 of f of t dt up here, we're going to go ahead and we're going to put a big old negative here, right? So we change this time by flipping it. And again, this will make more sense when we talk about volume and area. But right now, that's one of the properties we know. In order to switch a and b, we just have to put a negative out front of the integral. And so, ladies and gentlemen, when we're solving this problem, then all we really have to do here is do negative, and then we're going to go ahead and find the integration of -5 to -1. So -5 to -1. So that's going to be this triangle, and then which again is going to be negative, and I'm going to add to it the area of this trapezoid. So I'm going to go ahead and say, well, this is going to be 1/2, and then my base is going to be 2, and then my height is going to be -4, right? So -4. And so that's where this is going to end up being negative, and then it's going to be plus, and it's going to be our trapezoid, which I probably should have actually just get rid of all that so we can actually see the picture, right? It's really hard to see the picture here, what I'm doing. So let me make sure I got this right. So 1/2, and this is 2, and this is 4. So yeah. And so this trapezoid is going to be 1/2, because again, it's a trapezoid. The height of this trapezoid that we're doing right here, right? The height of this trapezoid is going to be the distance between the two bases. So 1, 2, 3, 4. And then we're going to add the bases. So this base here is 1, and this base here is going to be 2. And so let's actually do all the math for it. So it's going to be equal to negative, parentheses, well, this is going to be a -4, and this is going to be plus, and it's going to be 3 times 4 is 12, divided by 2 is 6. So I've got negative over negative, and then -4 plus 6 is 2. So this answer is going to be -2. So lots of good little problems here for that problem. Okay? So just remember the identity, that if you want A, be bigger than B. You didn't have to switch them, and that's one thing I will tell you guys. You don't absolutely have to switch them, but you can, just to make sure that it's easier reading from left to right. All right, so that's what we're going to do with that question. And then our final example, ladies and gentlemen, is number 12. 13 in our notes is total change theorem. And so I'd feel more comfortable doing this problem when we actually learn that. So we'll come back to that one later. All right, guys, so the last example we're going to do here is just an approximation, so it's another area on the curve thing. It says the flow of oil in barrels per hour through a pipeline on July 9th is given by the graph shown below. Of the following, that's approximates the total area number of barrels of oil that passes through the pipeline that day. So this is actually the first time we've done an example where we are actually kind of learning what integration is. So we want to know from 0 to 24, this is the hours of our function. We're going to say f of x dx. So I like the fact that we end on this one because, we've talked about approximation. It's not area. Our integration is not area. This is just how we find it. Just again, like we had in the derivative, is the slope of the tangent line. It's really not. It's a rate of change. So if we're trying to find the area on the curve, well, that's going to again be the rate of change this is. And you guys can see this. It's the total number of barrels that passes through the pipeline. So this is going to give us how many barrels went through between the hours of 0 and 24. Well, what we can do here is we can find the area of each of these little pieces. And so each of these little rectangles, it's going to be 6 times 100. So this is going to be 600, another 6 times 100, another 600, another 600. So the area, because we want the area underneath the curve, like we're looking for the area approximately under this curve. Well, we just go ahead and have this bottom part is going to be equal to 2400. So I know that these are going to clearly be out because I still got this little area up here to do. And this is why it's an approximation. We can kind of create a shape, a geometric shape that looks like this. And that geometric shape is going to be a triangle. Okay, again, because it's an approximation, so it looks a little bit weird. So this is going to be 1/2. Our height is going to be 100. And then our width is going to be 6 times 6 and 6, so it's going to be 12, right? It's going to be 12. And so this is going to actually equal 600. So we have to add another 600 to our problem. And so our answer is going to be D. Okay, D. So guys, that's a lot of videos for indefinite and definite integrals. And so in the next set of notes, we're going to talk about, finally, the fundamental theorem of calculus. So I'm hoping that makes sense for you guys, and I'll see you guys back in the next lesson.